Hello and welcome to Module 3.1, Representing Relations. This is our first module in Module 3, which is Relations and Functions. Our objective for today is that I can represent relations, I can interpret graphs of relations, and I can choose and interpret appropriate scales for axes and origins of graphs. So let's start off with vocabulary terms. A relation is a set of ordered pairs, and they'll be like this: parentheses x comma y, and there'll be a second one, x comma y, comma between them, and a third one, x comma y. Remember, it's always going to be the x value and then the y value inside of your ordered pairs. The domain is the set of first numbers. So first numbers in an ordered pair, they are the x values. They are also the input. They are what we are putting into the equation to achieve some sort of result. The range, this is the second number in an ordered pair. It is the y values, and this is the output. This is the result of whatever equation or formula that we're working with. And mapping. This is illustrating the relationship between the domain and range by showing how each element of the domain is paired with an element of the range. So let's just get started with example 1, and we're going to focus in on our ordered pairs. So we're going to first represent these as a table of values. And most of the time when you see a table of values, if it's oriented vertically, it'll be x values on the left and y values on the right, which we have indicated here. So we're going to start off with 2 and 0, 0 and 4, 3, -5, and -3, -5. Now, we said our domain was our x values. So we're going to start and list our x values. So we have a 2, a 0, a 3, and a -3. Our range is our y values. So we're going to start. We have 0, we have 4, and we have -5 twice. We are only going to list it once, though. And now we are going to draw our connections between our input, our domain value, and its corresponding range. So 2 is connected with 0. 0 is connected with 4. 3 is connected to -5. And -3 is connected to -5. We'll talk about what these mapping diagrams show specifically when it comes to functions at a later date. So now we're going to go ahead and graph our data points. So I'm going to start with my first ordered pair, which was 2, 0. Our x value is 2 and our y value is 0. So we go 2 to the right and we do not go up or down at all. And I do just want to highlight x values are the side-to-side axis, y values are my up and down axis. Now we're going to start with, we're going to go to the second point, which is 0, 4. So that means we're not going to the left or right any, but we are just going up 4. My third point is the point 3, -5. So we're going to go to the right 3 and down 5. And my fourth point is going to be -3, -5. So we're going to go to the left 3 and down 5 from my origin. And so those are my 4 points of this problem. So we're going to move down to our second problem, letter B. We have another set of ordered pairs, and we're going to go ahead and list them out. So the first one is -1 and -5. Our second one is 4 and 5. -2 is my x value, 3 is the y value, and 3 is my x value, -3 is my y value. So we list out our domain: -1, 4, -2, and 3. Our range values, we have a -5, a 5, a 3, and a -3. And I'm now going to just connect my dot, or connect my points. So 1 goes to -1 goes to -5, 4 goes to 5, -2 goes to 3, and 3 goes to -3. Now we're going to graph those 4 points on our grid here. My first point is at -1, -5. So I go to the left 1 from the origin and down 5. My second point is 4, 5. So I'm going to go to the right 4 from the origin and up 5. My third point is going to be to the left 2 and up 3. And my fourth point is to the right 3 and up or down 3. So the next two problems are ones for you to try on your own. Please do so, and then come back and check your work against mine. So for letter C, we're going to list out our values in our table here. So -4 is my x, 2 is my y. We have -3 for x, and we have 1 for y. We have 0 for x, -2 for y, -4 for x, -1 for y, 1 for x, 2 for y. So we're going to list all of our x values in the domain. So we have -4, -3, 0, -4 comes up again, and 1. We're going to list all of our y values. We start with a 2, we have a 1, a -2, a -1, and 2 repeats, so we don't add it again. So now we draw our lines. -4 is going to connect us with 2. -3 connects us to 1. 0 connects to -2. -4 is going to connect with -1. And 1 is going to connect with 2. And so we see some weird things going on here. And when we go on to module 2, or module 3.2, we are going to be able to see kind of what this is in terms of whether it's a function or not. So we're going to plot these points on our graph. So the first one is at -4 and 2. So we go to the left 4 and up 2. Our second point is at -3. So we go to the left 3, +1, up 1. Our third point is at 0 and -2. So we just go down the graph. Our fourth point is at -4, -1. So I go to the left 4, down 1. And my last point is at 1, 2. So we go to the right 1 and up 2. Letter D is asking us to write each set as an ordered pair. So we have -1, -5 as my first ordered pair, 4, 7 as my second, and -2, 3 as my third. For the middle one, the graph, we have to extrapolate or extract these points from our grid. So I'm going to start with this bottom one. We're going to go 1, 2 to the left. So that's -2. And we're going 1, 2, 3, 4 down, -4. Okay, we separate it with a comma. My next one, if I erase that, because we're going to go in a similar direction, we're going to the left 1, and we're going up 1, 2, 3. So that's -1, 3. And my last one, we're going to the right, 1, 2, 3, 4, 5, and we're going up 1, so that's going to be 5, 1. Lastly, if I look at my mapping diagram, my first point, 1 goes to 5, so we have an ordered pair of 1, 5. Then we have 5, and it goes to -1. And we have -6 that also goes to -1. Now, we have a couple more vocabulary terms. These two vocabulary terms are in a more applied context, and you will see these coming up in your science classes. The first is independent variables. These are the values in the domain, usually the x value, and it is the value that is subject to choice. You are making the choice of what this is measuring and how long you are measuring for. This could be measuring time if you're looking at distance, something's going. It could be temperature, or time if you're measuring how long a reaction happens in chemistry. So there's a lot of different options. This could be the hours that you are working, and the result would be the pay you get. So these are all of the things that you have control of in a problem. The dependent variable is the values in the range, usually y values, and it is the value that depends on the x value. So this one is the output. I'm going to do that in green. And it's dependent on the variable. It depends on the choices that you made. This is also the responding variable. So we could say responding variable. It is what is responding to whatever choice you made with the independent variable. This is what's going to be the outcome. So we're going to analyze some graphs now, and we are going to identify what are the independent and dependent variables of the relations, and then we're going to describe what happens in the graph. So my first one, we have this graph is representing the number of text messages sent by Nora throughout the day. So the first thing we need to identify is what is our independent variable, and that is our time. Independent variable is going to be time. Because we can choose, do we stop looking and measuring here? Do we stop here? Do we stop all the way at the end of the day? When are we going to stop? We are making that conscious choice of when we are going to stop measuring how many text messages she sent. And now the output, the dependent variable, is the text messages sent. As time goes on, the text messages are going to change. So now we need to look at each of the stages of this graph and figure out what could possibly be happening here in this context of text messages being sent over time. So I'm looking at this first segment and I see it's starting at 0 and we're going up. So I'm going to say this could be her texting on the way to school or in the morning. So she's got some time, she's texting on her way to school. Now we've got a flat section and we have another flat section. Well, if she's going to school, we know that our phones are expected to be in our lockers. So phone in locker. So that would mean she's not sending any text messages because she doesn't have her phone. It's where it should be, in the locker. Now, what about this section here where it increases for a short period of time? Well, maybe that is texting while she's at lunch, when she's allowed to be on her phone. And then our final segment here is going to maybe be texting at home, or it could be texting on the way home, something like that, after school at some time. Okay, so that would be the scenario that we're seeing in this problem. That is a possible explanation of what's happening for Nora's text messaging usage throughout the day. All right, now letter B asks us to analyze the orange segment and describe what is happening during this time. Well, our graph is giving us, we've got time on the x-axis and traffic congestion on the y-axis. So time, that is our independent variable. That is what we are measuring. We can look at the traffic over a period of time, and we are in control of what time period we're looking at. The amount of traffic, we do not have any control over. You have zero control over traffic. You are only responding to it. So we can measure how much time there was, but we have no control over what traffic there is. So when we look at this overall graph, right, this first segment, we see that it's pretty steady. There's really no change in the traffic. Then we have this spike going up, sharp increase. This could be something like the start of rush hour. As we get to 6:37 in the morning and the highways start to get crowded. Then we go with this horizontal section. So that means the amount of traffic congestion is not changing. There's a high level of it and it's not changing. This is your rush hour. Now, what's happening in the orange segment is the question that we're being asked. And in that orange segment, we could say the traffic is going down. So maybe this is when people are getting to work. So the amount of traffic is decreasing because people have already gotten to their destination. And then as we look at the final segment, we see an increase again. Maybe this is people going for their lunch break because it's not getting quite as high as it originally did. Or maybe people are leaving at different amounts or different times during the day, and we're seeing traffic starting to increase like that. All right, now we're going to look at a U-try problem. When an airplane takes off, its altitude rapidly increases. Once it reaches the desired altitude, it continues to fly at that level for a short period of time. Then the plane's altitude fluctuates slightly due to turbulence. Finally, the altitude decreases quickly as the plane lands. Which graph best represents this situation? Answer that on your own, and then we'll talk about it. Well, let's highlight each of these specific scenarios. In the first one, we increase rapidly, and then we just fly steady. There's no increase, no decrease, and we come back down. That doesn't really match the description of what we had. In the second one, our height increases, then we're steady for a little while, and then we have this jaggedness before coming back down. That certainly seems plausible for, going up and down, fluctuating slightly due to turbulence. Our third example, we have a slow increase in altitude. We're steady for a little while, and then a slow decrease in altitude. So this could be, maybe it's a training flight coming out of the DeKalb Airport. Maybe this is a flight from the big island of Hawaii to the island of Oahu, where Honolulu is, Pearl Harbor. So that one, you have a plane that's going to take off slowly, reach cruising altitude, and then slowly go back down, because that flight is only 35 minutes. Okay, in our last flight here, we've got a lot of concerns. We're going up quickly, we're steady for a while, but then we've got these huge swings in our altitudes before we come back down. I don't know about you. I really, really, really do not want to be on that flight, because those are huge swings in altitude and changes. That could be dangerous if you're seeing turbulence like that and you have the plane going up and down that much. That could certainly be very dangerous for the people on board. So those definitely don't seem to work for it. The one that is true is that second one there, where we have those slight fluctuations. All right, we're going to take a look at our next problem now. Example 3 and 4 is use appropriate scales and origins. So we're going to look at these data points, and we're going to try to figure out what kind of a scale should we use and what should the origin be. Now, scales are always a tough thing for 8th graders to work on, because you want to be able to represent all of your data points appropriately, but actually be able to represent them easily on the graph. So the way we're going to do this, we're going to look at what is my minimum and what is my maximum of each of my variables. Okay, so my minimum for my x variables, we have a 5, a negative 36, a 25, a 38, a negative 10, and a 1. My smallest x variable is negative 36. My largest x variable, well, that's 80, 48. Nope. Out of those, my largest x value, we have, looks like 38 is going to be our largest. Now, our y values, we have 80, 48, negative 91, 95, negative 50, and 22. My smallest one there is 91, negative 91. My largest is positive 95. So now, if I'm looking at this, we have a grid here that I've provided that is 10 by 10. 10 squares to the right of the origin, 10 to the left, 10 up, and 10 down. So if I'm looking at that, and I'm looking at my x values, I see that negative 36 and 38. Well, I'm trying to think of what can I divide 10 by that I can easily work with and still get to negative 36 and positive 38. And the value I think I'm going to want to break this down into is a scale of 4. So if we go every 4, so each grid is 4, we're going to have 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, right? So we're going up, and we're able to represent, we have 40 at the high end, we'll have negative 40 at the low end. But my x values, those are going to be able to represent all of our x values that we have. Now, my scale for my y-axis is a little different. I'm going from negative 91 to 95. So in order to fit all of that onto the graph, I'm going to say maybe I'm going to go up to 100 and negative 100, and I'm going to go with a scale of by tens. So we'll have 10, 20, 30, 40, 50, 60, 70, 80, 90. Now, when you label your scale, you do not need to label every single interval because that just gets messy, as you can see. The other thing that you should know about your scales, it should be consistent all the way across the axis. So you can't say you're starting at 0 and then you're jumping to 12. And then after that, it's 4. Doesn't work that way. You have to have the same interval all the way across the axis. Every hop you make has to be the same interval. If not, your graph and your data is not represented well. All right, so now we're going to go ahead and we are going to graph all of these points. Now, will they be exactly on grid lines? No, they're going to be approximations. So we're going to start with 5 and 80. So we're going to go to the right 5. So we're going to be just a little bit to the right of that first grid line. And we're going to go up to 80. So that's going to be right about there. Okay, our next point is at negative 36 and 48. So negative 36, that's going to be all the way over to the left. It's the second to last grid line. And up 48, it's going to be really close to 40 or to 50 there. So it's going to be a point like right that. The next point we have is 25 and negative 91. So we're going to go to the right 25. So 20 is this kind of boulder line. 24 would be the next one. So 25 is just past that. And negative 91, we're going to be, way down here. Our next one is 38 and 95. So again, we're going to be in between 36 and 40. We're going to be halfway there. And we're going to go to 95, which is halfway between 90 and 100. Now, you can see my dot didn't pinpoint exactly where I wanted it to go, but it's in that general vicinity. So I'm not going to be picky if you're here. Now, if you were in a completely different box, that'd be a different story. Next up, we have negative 10. So that's going to be between the second and third grid lines to the left, and it's going to be negative 50. So we're going to go down 5, and we're going to put a point in right there. And my final grid point is going to be at 1 and 22. So we're going to go to the right just a little bit, and we're going to go up above that second grid line, and it'll be right about there. All right. Now, as we look at the U-try problem, when graphing 1632, the ordered pair negative 10, 11, 4, negative 27, and 7, negative 5, what would be the most appropriate scale for the x-axis and for the y-axis? Now, we are going to assume we're going to use that exact same 10 by 10 grid that I have listed up above. Go ahead and try this on your own, and then we will go over it as a group. So we have min, max, and we have scale. So our minimum for our x values, my x values, we got 16, negative 10, 4, negative 7. So negative 10 looks like my minimum. My highest of those 4 numbers is 16. For my y values, my minimum, well, let's see, we got 32, 11, negative 27, and negative 5. So I'm going to get negative 27. And I'm going to have a positive, the largest of those is 32. So if I try to figure out a scale for these, my x-axis scale, if I'm going on a grid of 10, but I need to get up to 16, well, we could do a scale of 2, right? Because if we just went by ones, we won't get to 16. Going by fours is kind of overkill. So we can go by 2s on here. So that means we're going to have 20, negative 20 to 20 as my possible values on the axes. And now if I look at my y values, we've got to go from negative 27 to positive 32. Well, okay, again, we're kind of dividing this by 10. So that'd be like 3.2, 2.7 if we just looked at exactly to getting to those points. So let's go a little bit higher than that because going by 3s won't get us there. That would get us to 30, not 32. So let's go for a scale of 4. And that's going to give us going from negative 40 to 40, right? So you see what I did? I took my value, my highest value, and I divided it by the number of grid lines, and it would be 3.2. And I just don't like using decimals like that. I like whole numbers. So 3 wouldn't give us enough grid lines to get to our highest values, but 4 would. So I would round that up to the next value. And I did the same thing with 16, right? 1.6, I don't want to go by that, but I could, going by ones isn't going to work, so I would go by twos instead. All right, example number 5, interpret scales and origins. The average number of posts per day on a social media site each year is given in the table. Interpret the meaning of the axes, scale, and origin of the corresponding graph of the data. So we have the table here with all of our values. We also have a graph representing these social media posts. So now we want to figure out, first of all, what are the axes labeled with? So on the y-axis, we have the years since 2008. That is my axis. And what is our scale? It's 1 year for each grid line, right? 1 year post 2008 for each grid line. Now, my x-axis or y-axis, we have average number of posts per day. Posts per day. And we are going with a scale of 50 million. Okay. And it also asks us, what does the origin mean? So if we were to just zoom in on this graph, what does that origin mean? The 0, 0. What does 0 on the x-axis mean? What does 0 on the y-axis mean? So on the x-axis, the 0 mark is the year 2008. 0 on the y-axis would be 0 posts. Now, what do we know about social media? Well, in 2008, it was very much more limited. You may not know, but websites like Facebook at that point in time are still connected just to university emails. So the broader public is not able to access these. MySpace is just coming online in that just general time frame. But then as you see things going on, you see somewhere around 2013, 2014, things really start to spike upwards. And what's happening in that time frame? People have access to cell phones. And social media explodes as a result of the easy access to cell phones and easy access to high-speed internet that you start to see starting in that time frame. So that's where you see a significant increase in the amount of posts per day during these time periods. We're going to go to the next page where you are going to do a U-try problem. We have the United States Mint, which is responsible for producing and distributing circulating coins that are used by people every day to buy and sell goods. Facilities in Denver and Philadelphia produce billions of coins each year. The table and graph show how many circulating coins were produced each year at these facilities from 2001 through 2011. You are going to do the same task that we did the last time. Identify independent variable, dependent variable. No, not independent, dependent. You're going to tell me what the scales are and what the axes are representing, and then you are going to identify what the origin is. We could also talk about what independent and dependent variables are. Independent variable is the amount of time. Dependent variable is the amount of coins. So what year it is tells us how many coins were produced. So let's look at our x-axis. Our x-axis, and we don't have a scale printed here, but if we look at x right there, x is going to be our years, and that's years after 2001. And it's being measured in increments of 1 year. Now my y-axis, this is going to be coins produced, and we are going on a scale of 2 billion. So each grid line represents 2 billion coins being produced. Now let's figure out, what is my origin? Now the origin on the x-axis is going to be the year 2001. The origin on the y-axis is going to be 0 coins. Okay, origin on the x-axis, 2001, the year that we're looking at, origin on the y-axis, 0 coins. Now, let's just take a look at this. We see this huge dip in 2009. Anybody know what that's connected to? Well, in here, this is the Great Recession. So following the 2008 housing market crash, multiple banks went bankrupt, and you saw a recession, a significant economic downturn that affected the entire world. And it's exemplified right here in our data, where we went from producing 15 billion coins in 2006 to only producing 3.5 billion coins in 2009, because people were spending significantly less money, so there needed to be less coins in circulation. So we can see the economic impact of a recession even in the amount of coins that are being circulated. So coin collectors have trouble finding coins from 2009 and 2010 because they were significantly less produced than in other years around there. Those are our notes. If you have any questions, please bring them to class. Otherwise, have a great